So in this section, we want to go over a mathematical understanding of bias variance. We're going to do so with respect to another problem that you studied already, which is k-nearest neighbors. But did you know that k-nearest neighbors can be used for regression as well? Before going to understand the problem, let's look at what k-nearest regression does. Here's a sample where the target function is just plotted in black. We are sampling some points off of the target function, but with some noise. That's why you can see that the points don't lie perfectly on the curve. And with this sample, we can regress by taking the k nearest neighbors, here k equals to 3, and then zooming in here, we can see how it works. There's no training in k-nearest regression because just like any k-nearest thing, we just memorize the points and we use them at test time. So for example, here, we might look at these 3 points, and let's say we take a sample at this point here. This is a univariate function, so I'm just going to pick a particular value of x, okay? And I'm going to return back this particular value here because on this red segment, this straight red segment here, all of the x values on this straight x segment have these 3 blue points that I've circled as the nearest neighbor. Okay, so you can see what it's doing. It's basically doing some type of step function here where we're looking at the nearest neighbors and then computing an average of those 3 nearest neighbors to return. So let's take a look at the problem that's going to be specified. Let's assume that we have a observed target for a JF point, which is the true value plus some epsilon, where the epsilon is of standard form, right? Some Gaussian noise centered at 0 with unit variance of sigma squared. So this is pretty understandable. It's just saying that I have a point and I have some noise source nearby that's going to permute what I can see for the actual target. So this is a noisy target problem. Okay, using squared error laws, the expected prediction error of the regression fit, okay, which is being returned by the function at an input point of x0 can be written as the sum of 3 terms, the stochastic error, the bias, squared, and the variance. Okay, so because we're using squared error, we have this part where we're looking at the bias and we're squaring it. For the k nearest neighbor regression fit, the error can be expressed as follows. For some point, we're going to call that point x0. Okay, we're going to look at its nearest neighbors to get the actual value. Remember, like in 3 nearest neighbors, we'd find the 3 closest points and decide from there which the average value to return. So basically this is saying that I want to get the expected cost with respect to the observed target value minus the predicted target value. You can write a k here if we'd like, squared, right, because it's squared error. And this is going to be reduced. This is what we need to show, is it can be brought about in 3 different components. Okay, 1, 2, and 3. And we're going to define some terminology here. We have this particular term, xj, and what that just means is that when we move the index from 1 to k, we're getting the k nearest points to x0. So what we're going to show is that you can decompose it into these 3 parts of 1, 2, and 3, and it is exactly equivalent to the 3 terms that we saw in the last section, where we have one part that's due to stochastic noise, or the problem that we don't observe exactly what we like. There's some error or noise in the observation. One part that's due to bias, meaning that our representation using kNN can't exactly fit the target function. We saw that on this slide here, where the kNN is the red line. It's a little craggy, and the target function is quite smooth. And the last part being the variance meaning that depending on the particular data sample that we get or observe, because again, we have some noise in the observations here, we will have some variance. We won't be able to regress the exact values. So before we get started, the first term in the equation is really simple. It's just stochastic error. It's just the fact that our observations are going to have some error that are centered at 0 and with unit standard deviation. So that takes care of this first term already. We're done with that. What we want to do is show the two harder terms of the bias and the variance. So this is the stochastic error, and we're going to come back and show bias for this one and variance for this one. So bias, how do we get the bias term out of this? So we're going to start by deriving it. I'm going to say we have our y value for this 0th point, and what we want to do is integrate over our expectation of all of the possible data sets like we did last time. For the predicted hypothesis that comes from the k nearest neighbors for regression of this particular point. And because we are using squared error, we have to square it. So this is how we're going to write out the bias, right? Because the inner term here is the bias already. It's basically saying what's the difference between the observed value and the expected output of the classifier. And we're going to square it, right? Okay, and we're going to write this out. I'm going to take our y0 and propagate it over. Okay, and our expectation over the data sets. This is our script D. And we're going to expand this out now. And so, sorry, the square is the same square as before. It's going to be 1 over k for all of the summations. I'm going to make it narrow so we can fit it in, of k, j equals 1, y, x of j. We're cycling over all of the points and averaging them together to get out the value. Okay, and we're going to write that out again. I'm just going to copy the first part over. I'll do that quickly so we don't waste a lot of time. And we're actually going to look at this expected value. But the expected value for this term over here is actually very simple because the neighbors for point are assumed to be fixed in the problem. So since we have fixed neighbors, the expected value is actually the value of this. So we're just going to take the expected brackets and throw them away. Okay, so I'll just copy it out. Now I have a little bit more space. J. Okay, and that's going to be squared. All right. And then the next thing we can do is take all of our yi's and expand them. Remember, our yi, which is the observed value, is actually the target function with some noise applied. So we can write that out. So we're going to say our yi's are actually f of those points plus some noise value. And then I'm going to copy the second term. Oops. Okay, so this is over this part over here. And then we're going to square this entire thing because it's squared error again. So again, what we're doing is we're taking this y observation and expanding it out into the true target function and its epsilon. Right, so true target function and its epsilon. And what happens to all of these epsilon terms? What do you think is happening? Well, we're observing it over all of the possible data sets because we're not concerned about a particular data set point. This is the bias. We're not talking about a particular one, but over all of the data sets. So when you think about integrating this type of Gaussian noise source over all of the data sets, they're going to go away, right? Because they're all centered at 0 anyways. They have 0 mean. We are going to end up with this, right? Which is the expression that you saw on the slide, right? So it just takes those two terms down, and we end up with a form that's exactly like what we set out to build. So we're done here. So we finished our bias squared. That was this term. And we're done with that. Now we want to do the variance. Let's write it down. So we're trying to look at the variance of the predictions on made by the classifier on the point x0. And what does that equal to? Well, it's going to be the variance of the prediction itself. So we can write out the prediction, which we know because it is basically the average of all of the k nearest neighbors. Well, we can certainly write that out, right? So we are going to go from j equals 1 to k for all k nearest neighbors, like for example k equals 3, and just take the value that we're going to predict, which is basically whatever values are for those particular neighbors, right? Okay. And then what we're going to do is look at this variance, and we can take a note of something important, which is the variance of a variable against a constant. We can factor out the constant. So we're going to take use of this particular rule for a variable and then say it's basically so we're going to treat that so this is because the expectation of the constant times the variable is the same as the constant times the expectation of the variable. So I'll just write that as well. Oops. So here we have a constant and we have the variable that we want to look at, so we can apply that right away. So we're going to take 1 over k, 2 points of that, right? So it's 1 over k times 1 over k, so 1 over k squared, and then the variable itself. And here's the variable that we're looking at, which is just the expansion of y, which we're going to write out now. Let's make that j nicer, and the epsilon with respect to that point. Okay, so we can further write this out. Let's switch back to red here. This step is pretty, this step is pretty okay. We are just going to factor the variance into the two parts because they're independent of each other. Okay, and just like we saw before, we're going to make use of this assumption that the points that are the neighbors of the point in question that we're looking at, x0, are fixed, so the variance is not there. So what's next? Since the variance for this middle term goes away, then we're left with this. Just the last term. And hopefully we know what this means. We are going to sum over all of these, so we're going to get another factor of k here, and that's going to cancel out. So we're going to get the variance of a data point, which is just sigma squared over k. And we're done with that. And so finally we've gotten our last term here. We'll check that off. And so we've checked off all three of these, so now we're finished.